Welcome, everybody. It's great to see the enthusiasm. This is the second Misner lectureship that we'll have had in the department. This is a lectureship set up by donation from Charlie Misner's family, actually. And it'll happen once every 2 years. We had one already, and that was given by Sam Gralla. And it was about imaging, black hole imaging, including the images that we saw from the Event Horizon Telescope. So in addition to a public lecture, the Misner Lectureship invites preferably on the younger side scholar to our university to give some also technical lectures to experts in the field. And our current Misner Lectureship did that. I'll mention in a second what he spoke about. But just first, the Misner, Charlie Misner, we called him Charlie, Charles Misner, got his PhD in Princeton University in 1957. I think, and Dieter Brill can correct me if I'm wrong, he was the first PhD student of John Wheeler who worked on general relativity. Is that right? He thinks so, okay. His PhD thesis was called Feynman quantization of general relativity. That was a pioneering contribution in a field that actually remains one of the key approaches to trying to understand the combination of quantum mechanics and general relativity. Remains central to much cutting-edge research, and actually, even after all these years, it also remains somewhat obscure. So Charlie worked not only in quantum gravity, but in classical, and did foundational work in both areas. He also worked on black hole astrophysics and also cosmology. So I think that our speaker today, Daniel Harlow, is a perfect choice for the second Misner Lectureship. Daniel got his PhD at Stanford University in 2012 and did postdocs at Princeton and Harvard. And since 2017, he's been a professor at MIT. And his research area is also not only general relativity, he works in classical and quantum field theory, including, but not limited to gravity. He's a winner of the New Horizons in Physics Prize in 2019 for work on quantum gravity that's, I believe, quite related to things he'll be telling us about today. He spoke yesterday on puzzles and some answers, or proposed answers, of quantum cosmology, and this morning on a gnarly technical point in quantum field theory that was very illuminating. In this public talk, he will share insights and progress over the past decade on puzzles of black holes and quantum gravity. Thank you, Daniel.
Thanks, Ed, for the introduction, and thank you also for the invitation to the University of Maryland. It's a pleasure to be back here, actually. I was based here for a year back in 2018, 2019. Lots of familiar faces again. It's also nice to be celebrating Charlie Misner, who, of course, I've been inspired by many of his famous papers, the ADM energy, for example. Also, actually, just last year with a student, we were reading a fun paper by Misner, I think that was called Cow Nut as a counterexample to almost everything. And it somehow was relevant for a paper that we wrote. There's something in there that's called Misner space. So today, I'm going to talk about this rather general sounding topic, quantum mechanics, black holes, the emergence of space and time. We're going to talk about a couple things. So we're going to say some things about quantum mechanics, which hopefully you've at least heard of, which is the somewhat strange theory that controls how matter behaves at short distance scales. We'll talk about black holes, which are astrophysical objects that are so dense that light cannot escape from their gravitational pull. We'll talk about quantum gravity, which is the problem of finding a theory of the world that combines quantum mechanics and gravity, which is a problem that's 100 years old and we still haven't solved it. And then we'll talk a bit about quantum computers, which are, I used to say hypothetical devices. I'm not sure hypothetical is quite right, but on the other hand, we don't quite have them either. But we have sort of, we have, infant quantum computers now, so I'll just call them devices, which harness the power of quantum mechanics to do useful things. And for example, to solve computational problems which would be intractable on a conventional computer. And so what we'll see, so this seems like a bunch of different topics, right? But actually we'll see that in order to understand them, we're going to need to combine all of them, and that's what makes it fun. And so indeed we'll see that to come up with a sensible theory of the first three things, we need to think that space and time themselves, which we usually think of as austere arena on which physics happens, are themselves emergent notions. They're only true in certain situations and in some approximation, and more carefully they have to be replaced by something completely different if we want to have a more robust theory. And we'll see that in trying to develop a language to talk about the emergence of space and time, it will be useful to use ideas from the theory of quantum mechanics. And so that's where we're going. Hoping it doesn't sound too scary, I'll try to keep it comprehensible. I'm aiming for a broad audience here, so if you're a physics expert, I apologize if things go too slowly, because this talk is not aimed at you. On the other hand, it's not aimed at my 7-year-old either. So it does have a few equations here and there, a little bit of calculus maybe, but nothing too scary, I hope. Okay, so here we go. So we're going to start at the beginning with classical mechanics. So here's an equation. Anyone, raise your hand if you've seen this equation before. I think we'll just make sure I gauge the audience. Okay, so classical mechanics is the theory of the world where you say that the world consists of a bunch of particles that are on trajectories x of t, where x is a vector. And your goal in classical mechanics is to find x of t, given the initial positions and velocities of all the particles. And you do that by solving Newton's equation that the force, which is a function of the locations of the particles and their velocities, is equal to the mass times the acceleration. Okay, actually, there should be an I on the mass there, because the particles don't all have the same mass. So, for example, here's a not very accurate picture of what's happening in the solar system. Here's the sun, here's the Earth, and Earth is moving in an orbit around the sun. And the reason that the Earth isn't just flying off into space is because there's a gravitational force which is pulling on the Earth towards the sun. And the force is Newton's constant times the product of the two masses divided by the length squared. So that's classical mechanics. So that's sort of the first half of high school physics, or the first half of first year physics at UMD. The second half, you learn about the electromagnetic force. So that's an example of a force within classical mechanics, which is a force that controls the interactions between particles that are charged, like electrons and protons. So in essence, the way that the electromagnetic force works is that each charged particle, here's the one with positive charge, here's one with minus charge, it kind of sprays an electric field out of it, which kind of establishes the electromagnetic environment around the particle. And then other charged particles react to that force. Via the Coulomb force law, or maybe also the Lorentz force law, if we include the magnetic field. So far, so good? Now, that's all well and good. That's what most of us learned in high school. That was the state of physics, more or less, at the beginning of the 20th century. But if you want to understand the world in a way that is consistent with everything we see around us in this room, then classical mechanics is not enough. It's not enough to be classical. So let's give a simple example of why not. So let's think about the hydrogen atom. So maybe in junior high school or whatever, when you first learn about the hydrogen atom, this is what you learned. You learned that there's a proton in the center. And then there's an electron that's orbiting around. It looks pretty similar to the solar system picture that we had on the previous slide. Anyone believe this picture?
I don't think it's a scale line.
Yeah, this picture doesn't, it's a nice picture, but it doesn't work. And the reason is that this electron is a charged particle and it's accelerating, right? It's feeling a force towards the center as it goes around. And in electromagnetism, if a charged particle is accelerated, then it radiates, right? That's how an antenna works. The charges accelerate up and down, and that makes the radio waves that people in ancient times used to listen to on these devices called radios. And if you could do a little computation to estimate how long does it take. Well, so when it radiates, right, it loses energy, and so the electron has to spiral into the center. And if you compute how long does it take to spiral into the center, it's about 10 to the minus 10 seconds. And then the hydrogen atom is gone. And last I checked, that's not what happens to hydrogen atoms. I have never seen one do that. I don't think any of you have either. And so somehow we need a better theory than this of what's going on in the hydrogen atom. Here's a related puzzle. So maybe you saw some picture when you learned about solids. Like say, here's a picture I found online of salt. Okay, don't ask me which one is the sodium and which one is the chloride.
Big one of sodium.
Yeah, this picture doesn't make any sense either. It's classically, because it's actually a theorem that you can't have a stable configuration of charged particles at rest interacting by Coulomb forces alone. If you put a bunch of charged particles like this, the thing would just fly apart. Whereas again, I haven't seen that happen with the salt on my table. And so we need some kind of new theory to let us have salt. So the theory that we need is quantum mechanics. So and the resolution of this is that we have to replace classical mechanics by quantum mechanics, both of these puzzles. So here's how it works. Okay. Don't worry too much about the details about this, but it's good to see it once, at least a little bit. So, in the classical picture of the particles, the state of the system is determined by knowing the positions and the velocities of all the particles right now, right here. Okay, right here, right now. In quantum mechanics, and I'm not going to try to explain why this is true, I'm just telling you what the rule is. The rule is that to know the state of the system, instead of saying all the positions and velocities, you instead just give a function psi of all the positions, which is valued in the complex numbers, right, including the square root of -1. Okay. For any configuration of, set of positions of all the particles, this function gives you a complex number. And in quantum mechanics, that's the state of the system. It depends on the positions only and not on the velocities. We'll see in a moment why this helps us. Now, why would you do such a silly thing? Well, what happens, what does this sign mean, right? What it means is that if you take its absolute value squared, that gives you the probability density for where you find the particles. So if you want to find particle 1 in position x1, and particle 2 in position x2, and so on, then you take this function, evaluate it at those positions, and you square it in absolute value, and that gives the probability of where the particles are. Now, since I said it's complex value, right, there's also a phase, right? It's not just the absolute value, right? There's also this sort of direction that the complex number points in the complex plane. And that has information about the velocities of the particles, right? You may wonder where the velocities were if they're not, in the wave function, and somehow they're in the phase of the wave function. And that leads to this funny thing that the more you know about the positions, the less you know about the velocities, which is called the uncertainty density. So that's non-relativistic quantum mechanics in one slide. Now let's see how this helps us with hydrogen. What happens is that the lowest energy state of hydrogen, so before, right, it was just you put the electron right on top of the proton, right? It radiates away its energy, it falls down to the center, and that's the lowest energy state, is the electron right on top of the proton. In quantum mechanics, instead, what happens is that the electron is kind of spread out by this wave function in a rotationally invariant cloud, so this proton is at the center here, and then the probability distribution sort of gradually falls off as you get away from the location of the proton. And the reason, so it can't just be at the center by the uncertainty principle, right? If it was at the center, then we would know its position exactly, and then we wouldn't know its velocity at all, and then it would fly away from the center immediately. Okay? So there's a tug of war between knowing the position and knowing the momentum, and that forces the wave function to be spread out around the center of the hydrogen atom. And moreover, since it's spherically symmetric and static, right, it's just sort of equally likely to be anywhere, it's not actually doing this. And so it doesn't radiate. And that's how quantum mechanics makes the world safe for the hydrogen atom. There's a similar story for salt, but it's more complicated, so I'll try to explain. So good, that's undergraduate quantum mechanics. Now on to graduate quantum mechanics. So there's also this thing called special relativity that says that you can't go faster than the speed of light. Okay? And you know, in the classical Newtonian gravity, right? If you have you know, the sun and the earth, you just say there's a force between them that's sort of instantaneous. And if you somehow remove the sun, then the earth would know immediately and stop you know, pulling towards it. And that's faster than light, and that's not allowed. So we need some way of doing quantum mechanics which is consistent with relativity. And so it turns out to be a good idea to, instead of applying the quantum mechanics just to the locations of the particles, you should apply it to the fields like the electric field as well. You should say the electric field itself also has a wave function, and it has fluctuations, and so on. And you know, essentially the reason why you want to do this is because you want to say, if I do something here right now, the news that I did something needs to propagate at some finite speed, which is slower than the speed of light through the system, and it does that by being a ripple in some field. And in fact, light is a ripple in the electromagnetic field that we talked about before. It moves at the speed of light. But in relativistic quantum mechanics, everything has to be a ripple in some field. The electron has to be a ripple in some field. You know, the proton has to be a ripple in some field. So this theory of quantized field is called quantum field theory. And our best theory of physics so far, the standard model of particle physics, is a quantum field theory. Okay? And here's a picture from the Large Hadron Collider. I think this is supposed to be an event where the Higgs was produced. I don't know. Does anyone who knows about this stuff want to check me? I think that's what this is. And this is data. I checked, it's not a simulation. This is data.
I think I've seen it in the same Wikipedia page.
But I think I got, yeah, maybe it's Wikipedia. Yeah, I didn't get it from Wikipedia, but probably. Yeah. Right, so the standard model of particle physics is a very successful theory. We've tested it many times. It always still works. Here's an example of it. Now, the crucial principle of quantum field theory that makes it consistent with special relativity is the principle of locality, which is the idea that if you look at the fundamental degrees of freedom of the laws of physics, you know, the things that can be in this state or that state that make up the actors in the laws of physics, those things, there's an independent one of them, or actually more than one of them, at each point in space. Okay, so here I've drawn a cartoon of space, and these red dots represent kind of different points in space. And for example, there's the electric field at that point, and there's electric field at that point, and also at that point. And I can adjust those independently, right? Just because I change one of them, I don't have to change the other one. Actually, the electric field is a slightly bad example for that because of gauge invariance, but ignore that unless you know what I mean. And moreover, when they interact, right, this little red dot here, when it interacts, it can only interact with its immediate neighbors. There's no interaction between this one here and that one there. Because if there was, then there would be interaction between my office in Cambridge and this room, and then that interaction would allow the fields to talk to each other immediately, and that would be faster than light, and that would be bad. Because we want to be consistent with special relativity. So this principle of locality is the principle that the degrees of freedom here are independent of degrees of freedom there. Now, this principle has an interesting consequence. It says that if we put a quantum field theory in some finite spatial region whose volume is V, like we look at all the fields in this room, and we ask how many degrees of freedom are there in this room? Well, it's proportional to the volume, because each point gets its own degree of freedom. Now you could complain that, okay, it's proportional to the volume, but really it's infinity because the number of points in this room is uncountable. And then you have to say, okay, but discretize it some short distance scale, because who knows what's going on in short distance scales anyway, and then it grows like the volume. And so, in low energy states of a quantum field theory, these degrees of freedom, these local degrees of freedom at each point in space, are undergoing fluctuations, just like what we saw for the hydrogen atom, right? We saw that the electron in the hydrogen atom, its position was not definite in the lowest energy state. It was kind of in this spherically symmetric cloud. So each time you measure the position, you might find it in a little bit of a different place, and the same for its momentum. And the same is true for the electric field. Okay, the electric field right here, right now, is fluctuating, even in the ground state, the lowest energy state of the system, because of quantum mechanics. Okay, so that's it for quantum field theory, so now we're done with graduate quantum mechanics. On to gravity. I have to put all the pieces together before we can start playing. We have to first kind of build up the cast of characters. So now let's go back to classical mechanics for a minute. Okay. So hopefully you learned at some point, or you just feel intuitively, that if you have a massive object like the Earth, and you jump up off of it, if you jump fast enough, there's some finite velocity where if you could reach it, you would just launch off into space and not come back. And that's called the escape velocity. And when you build a rocket and you want to go to the moon, your goal of building the rocket is to get to the escape velocity. And so here's a formula for the escape velocity, if you like formulas. You can derive this formula yourself by setting the kinetic energy that you jump when you jump equal to the potential energy that it would take to get out to infinity, and that's the escape velocity. And you find that it's the square root of twice of Newton's constant times the mass of the Earth divided by the radius of the Earth. And so, kind of makes sense, right? If you make mass bigger, the escape velocity gets bigger. It's harder to escape, right? It's harder to escape from Jupiter than it is to escape from the Earth. Okay. On the other hand, if you fix the mass and you make the radius smaller, then it's also hard to escape, because if you compress the Earth a little bit, you'd be deeper in its gravitational field and you'd have to be going faster to get out. And in fact, you can see that if we keep the mass of the object fixed and we decrease its radius, we can make the escape velocity as large as we like. Right? We can just look at this formula. Right? I fix it, g is fixed, it's a constant of nature, and then I just take r smaller and smaller, the escape velocity gets bigger and bigger. At some point, we're going to get into trouble, because eventually that escape velocity is going to reach the speed of light. And that's going to be the situation where now nothing can escape from the gravitational pull of the object. So that happens. So if we look at our magic formula here, right, we want the left-hand side to be equal to c. And so that gives us a formula for r in terms of m. And the formula is that r is equal to 2gm over c squared. And that's called the Schwarzschild radius for the mass m. Right? Given a mass m, then g and c are fundamental constants. And so then this gives you a radius. And you can work out, right? So for the Earth, the Schwarzschild radius is about a centimeter. Okay, so if you could take all the mass of the Earth and compress it down to a little ball that's a centimeter in size, that would be a black hole. Right? That would be something that you couldn't escape from. For the Sun, if you took all the mass and compressed it down to the Schwarzschild radius, it'd be about a kilometer. And indeed, since nothing can move faster than light, if you compress a massive object to within a Schwarzschild radius, you get something that nothing can escape, and that's what we call a black hole. Right. So far, so good? We're just going to keep building and building here. So for a while, black holes were considered to be somewhat fanciful. Einstein didn't believe in them, for example. These days, we see them on a regular basis. I put see there in quotes because you never really see a black hole in that black hole. But we see pretty strong evidence that there are black holes all the time. Well, I don't personally because I'm a theorist. My friends who are real scientists. So here are two examples. This is an image of a black hole from the Event Horizon Telescope. Actually, this black circle is not quite, it's bigger than the Schwarzschild radius. I think it's like a factor of 6 or something. So the true Schwarzschild radius is a bit smaller inside of there. And all this orange stuff is the accretion disk of matter forming a black hole. And this is, I think it's M87, a giant elliptical galaxy with a supermassive black hole in the center, and it shoots this gigantic jet out of it. And in fact, I think this picture is the picture of that black hole. The one that's firing out this relativistic jet that goes over thousands of light years. Right? This jet here, thousands of light years. Pretty nuts, right? So classically, we actually understand black holes quite well using Einstein's theory of gravity, which is called general relativity. General relativity says that gravity arises from the curvature of space and time. It's a beautiful theory. We could easily spend a whole hour celebrating general relativity. In fact, arguably we should, since it's the Misner lecture. And Misner is one of the founders of the modern understanding of general relativity. But on the other hand, unfortunately, I'm kind of saying here that we already understand it quite well. And as a theorist, I like to think about things that we don't already understand quite well. But this picture here is some cartoon of the curvature of space. I'm always hesitant to show the picture because it's actually wrong. The orbit of the sun, of the Earth going around the sun, really comes from the curvature of time, not the curvature of space. But it's such a nice picture. This is like a totally respectable picture. This is from LIGO. So this is a signal of two black holes merging and producing gravitational waves, which you can compute that signal using numerical general relativity, which works very well as far as we know, at least according to my stuff for a living. So classically, black holes are in pretty good shape, despite the fact that they're kind of crazy. All right, now we bring back quantum mechanics. So quantum mechanically, I would say black holes are still quite mysterious. There are many things about them that we don't understand so well, and so I'm now going to try to share my confusion with you. So this picture, I won't try to explain this picture in too much detail. This dashed line here is the horizon, it's the edge of a black hole, so everything on this side is inside, everything here is outside. That's all you really need to know about this picture. But the important consequence of this picture is that once you include quantum effects, black holes radiate with some temperature T, which is called the Hawking temperature. Here's the formula for the Hawking temperature. It's h bar, Planck's constant, times c divided by 4 pi times the Schwarzschild radius. In principle, I think I should put a 1 over Boltzmann's constant there, but I just can't bring myself to write Boltzmann's constant. Execrable thing. You should just measure temperature in units of energy. I mean, I don't want to write the h bar and the c either, but okay. It's a bridge I won't cross. So why do black holes radiate? Well, it's because of these fluctuations of the fields that we talked about before, right? So remember the quantum field, there's an electric field, say, or a magnetic field, whatever, right here at the edge of the black hole, and it's undergoing quantum fluctuations. So it's kind of not quite in a definite configuration, like the position of the electron in the hydrogen atom. It's kind of spread out a bit in what it's doing. And near a black hole, some of these fluctuations can leak out because sort of half of the fluctuation ended up inside and the other half ended up outside. And then the part of the fluctuation that's outside kind of leaks out to infinity as radiation in a way that Hawking was actually able to compute in this incredible paper that he wrote in 1975. Like of all the papers that I have physics envy about, like this one is #1. It's just an masterpiece. It's even better than Einstein's papers about general relativity, just to read. Well, maybe just partly because I don't read German. Now, if a black hole has a temperature, right, it, radiates at some finite temperature, then by the first law of thermodynamics, so who's heard of the first law of thermodynamics? The high school chemistry, at least, right? Yeah, so the change in energy is equal to the temperature times the change in entropy. That's the first law of thermodynamics. And so then if you know the temperature as a function of the energy, which is just mass of a black hole, then you can integrate to get the entropy as the formula of the mass. And the formula you get is that the entropy of a black hole is equal to the area of its edge, its horizon, divided by 4 times Newton's constant, times some of these annoying things that you should set to 1. So it's the area of the horizon. That's the important. Now, on the one hand, this is really a quite large entropy because, well, h bar is pretty small, and g Newton is pretty small, and those are both in the denominator. And if you compute this, for example, for the largest known black hole, whose mass is about 10 billion times the mass of the sun, real monster, you find that its entropy is actually bigger than the entropy of the rest of the observable universe, not including black holes, which is dominated by the cosmic microwave background. Okay, so if you look at all the CMB, the cosmic microwave background in our whole observable universe, it's less than the entropy of one black hole, for example, the one sitting in the center of M87 that was producing that really long jet. And so that's really kind of nuts when you think about it. On the other hand, it's kind of small, this entropy. And that's because, if you think about how it scales with the size of the black hole, it scales like the surface area of the black hole. Right? Whereas in quantum field theory, right, we said that the number of degrees of freedom scales with the volume. Okay? And if you think about areas in volumes, right, like if you have a cube of length L, then the area is of order L squared, 6L squared. But the volume is of order L cubed. And so if L is big enough, then the cube beats the square, and the volume is bigger, and that's more entropy. Okay, so for sufficiently big black holes, the area is smaller than what you would have gotten by trying to compute the volume inside. Yes, indeed, that's what I was going to say. Yeah. So for sufficiently large regions, the volume is bigger than the surface area. And so somehow, in a quantum theory of gravity, where black holes have entropy, there are somehow fewer degrees of freedom in a region are present than what you would have gotten from the principle of locality that said that it had to scale with the volume. And so that's kind of our fundamental problem, is that black holes don't have enough degrees of freedom to account for everything that fits inside. And Hawking pointed out that this tension is particularly bad if we let the black hole evaporate. So remember, it's radiating at some finite temperature, so it's losing energy, its mass is decreasing. So as it evolves, what happens is that the volume inside actually grows with time. I didn't tell you enough about black holes to see that, but if you think about the black hole, you can see that it's true, because even though the area is shrinking, the length is getting longer. But the area is shrinking. And so eventually, to have a reasonably local theory of the interior of the black hole, you need to fit more and more eggs into fewer and fewer baskets. Okay, the horizon area just keeps getting smaller, and the interior keeps getting bigger and bigger, and what are you going to do? Like, is the interior of the black hole even going to remotely look like these local quantum field theories we were talking about before, where you have independent degrees of freedom at each point in space? And so that's sometimes called the black hole information problem of Hawking, although that's not how it's usually presented. So indeed, we see that in order for quantum black holes, to have quantum black holes that make sense, the local picture of space-time, having independent degree of freedom at each point in space, is just totally wrong, at least in the black hole interior. Locality must be an emergent phenomenon that happens only in some situations and in some approximation. And that is our task for the rest of the lecture, is to figure out what kind of a theory makes sense where it sort of behaves like it's local for simple things, but then somehow actually has many fewer degrees of freedom than you might have thought. Okay. So this should be like the point of maximal confusion. So I'll now try to start developing the tools to think about this a little more precisely. So, first let me mention this idea called holography. So back in the early 90s, the famous Dutch physicist, okay, maybe we can try to get Gerard and Troop, a Dutch person can tell you how to say that. And also my PhD advisor, Lemon Tuskin, proposed a somewhat crazy way to solve this problem. And the proposal was the following. They said, we think we're living in 3+1 dimensions, right? 3 space and 1 time in this room right now. But actually, we're not. The fundamental description of what's going on in our universe is really 2-dimensional, and it's living off at spatial infinity. Sounds totally crazy. It's off the boundary of space. So, we think we're in 3D, but really we're in 2D. Now, one way to argue for this is the argument basically that they presented, is you say, well, if you consider some region of spacetime, what's the most entropic thing you could put in that region of spacetime? Well, it's got to be a black hole. Because if you fill that region of spacetime with a black hole, if you now try to throw anything else in there, it'll just make the black hole bigger, because it'll make it heavier. Remember, the Schwarzschild radius gets bigger with the mass. So the black hole is the most entropic thing you can have, and that must mean that the fundamental degrees of freedom, the number in that region is just the entropy of that black hole, which is the area of its horizon. And so if you want to know how many degrees of freedom there are in all of space, you consider sort of an infinitely big black hole. And then you just get the horizon off at infinity, and then that's the number of degrees of freedom. They're all just living out there at infinity. So Lenny called this the holographic principle because, a hologram is like a sort of 2D image of a 3D thing. And as you can imagine, maybe this wasn't taken so seriously when it was first proposed. I mean, I get emails, a few per day with some sort of crazy theory from some random person around the world. Some of them don't sound too different from this. Okay? So I wasn't around in the field then, but my impression was that serious people at places like Princeton, right, were kind of sneering a bit at this when it came out. The situation changed dramatically a few years later, though, when this guy named Juan Maltesano, who's from Argentina, who's now a professor at Princeton, found an explicit example of the theory of quantum gravity, which was manifestly holographic, which is this thing called the ADS-CFT correspondence. So what's that? Here's what it is. The details don't matter too much. I tried to use this picture in an article I wrote for the MIT News, and the lawyers wouldn't let me because they said I would be sued for having Escher here without paying me his estate. Here I am doing it. If the President of the United States is allowed to violate the law whenever he wants. That's probably not how you're actually supposed to respond to fascists. Okay, so this Escher picture, right? So this is a space-time that has negative curvature, right? That's what this picture is famous for. Is it shows what it's like to live in a space that has negative curvature. So if you look at these white lines here, they're parallel, but they bend away from each other. That's what So on the Earth, right? There's positive curvature. So if we start parallel here, going this way, because of the curvature of the Earth, we eventually come together. Okay, so that's positive curvature. In negative curvature, parallel lines diverge from each other, and that's what this picture is showing, right? And so in fact, all the fish in this picture have the same size, although they don't look like it. So, and what we learned from Maltesano is that if you do quantum gravity in this kind of funny negative curve space, it's actually equal to some totally conventional quantum field theory that lives at this boundary of the space. So in this picture, space is two-dimensional because it's hard for me to draw a three-dimensional version of the Escher thing. Okay? And so then the spatial boundary here is one-dimensional. It's this circle, and these dots here are like those red dots in the lattice picture I had before. It's independent degrees of freedom in each one of these black dots. Okay? And the wonderful thing about this is, this is super scary. It's quantum gravity. They're black holes. Space-time is emergent. Who knows what's going on? But over here we have good old quantum field theory with no gravity, the kind that we test at colliders every day, and we understand it pretty well. We could still understand it better, of course, I have to say that just in case anyone here is working with something. But we understand it much better than we understand quantum gravity. And Maldacena told us this thing we don't understand is equal to this thing that we do understand, and that sounds like progress. And it also supports this idea that indeed the fundamental description is all living in spatial infinity, and what's going on in the middle here is somehow emergent, right? That space-time isn't really there, it's just built out of these fundamental degrees of freedom at the edge. Now, there are some immediate questions that you could ask about this, though. Like, how can this possibly work? Okay, that's the first question. That's right, that is the first question you should ask. Good for you to ask. So, let me try to ask that a little more precisely. So if locality is really only emergent, right? If what's really going on is this stuff at the edge, why does it look like this picture? It's such a good approximation. In this room right now, locality feels pretty good. Not just in this room, it works pretty good at the LHC, it works pretty good in every experiment that we've ever done. Okay, so how can it be wrong so drastically? Okay, so that's question number one. Maybe an even more refined version of that question is, if you look at that picture of the Escher, the degrees of freedom in the middle of the fish, right, are different. There are different spatial points from the degrees of freedom at the edge, and locality would say therefore they should be independent, but they can't be because the boundary degrees of freedom are all there are. Okay, so somehow what's going on in here can't really be independent of what's going on at the edge, but it has to behave like it to a very good approximation. It has to fake that it's independent to a very high level of accuracy, because otherwise we would have seen it. So after the correspondence was discovered, people spent quite a while, doing calculations and having fun. But this basic question of how can this possibly make sense, at least in my view, was not addressed in a convincing way. At the time around when I was finishing my PhD in 2012. And so I and my collaborators in 2014 sort of set out to see if we could understand this and come up with some mathematical theory of how can you fake locality, starting from a boundary theory. Now, in order to explain what we learned, we've got to do another detour and lift a few more weights and build a few more muscles. We've got to learn a bit about quantum computing, because that's going to give us the tools we need to answer this question. So, let's start with the basics. What is a computer? You may feel you intuitively know that. Computers used to be people, actually. You know that? There were people. There was a room, and there were people inside, and they were called the computers. Actually, they were often women in NASA. Calculations would be fed in through a hole in the door together with some food, and then this would be after a while. And indeed, those were computers. They were computers, right? And why? Because at the most basic level, a computer is just a device that processes information. Given some data that we put in, it applies some sequence of simple operations to the data, and then it gives us some output data. Hopefully with the answer to the question that we asked. We didn't put a bug in the program. So, for example, we could give it two integers and we could ask for their greatest common denominator, or we could give it a picture and ask whether or not the picture is a cat. Okay, those are both tasks that we could ask the computer to help us with. For a conventional computer, the data we put in and the data that we get out is encoded in binary digits, which are called bits, right? Zeros and ones. And then what the CPU does is it acts on the bits using simple arithmetic operations. For example, it says, if bit 10 is 1, then flip bit 20, but if bit 10 is 0, then do nothing. That's an example of what's called a logical gate, and the CPU just executes a sequence of those logical operations following the instructions from the program. And even though each step is kind of trivial, like that, right, they can build up to something remarkable. So here's a cartoon. Here's the picture. It converts it into bits. You give the bits to the computer. It comes out. It says, yes, that's a cat. Now, in computer science, there's a fundamental task, question, which is which problems are easy and which problems are hard. Okay. So the way you formalize this is you ask how many of those fundamental arithmetic operations does the CPU have to do to turn the input into the output, right? And so for some easy calculations, it doesn't have to do too many, but for hard calculations, it may have to do a lot. So for example, say I have two n by n matrices, A and B. And what I want to get is I want to get their matrix product A times B. Hopefully matrices are okay for most people. So, well, to compute A times B naively, what you have to do is for each component of AB, you have to multiply n pairs of numbers and then add them up. So that's 2n operations for each component. And then there are n squared components, so that sounds like 2n cubed operations to multiply two matrices. So usually in computer science, people don't care too much about the two, they just care about the asymptotic scale. So they say it's order n cubed. You can multiply matrices in a time which is order n cubed. Actually, you can do it faster. Does anyone know that you can do it faster? So I think the current state of the art, by reusing some of the multiplications and additions, is you get it. Very dramatic. Okay, so you can get this down to about 10 to the 2.3. Okay. Don't ask me how. I have no idea how. If you're clever, it's not n cubed, it's faster. You reuse some of the multiplications and additions. But either way, what a computer scientist would say is that this is an easy problem because it can be solved in polynomial time. The running time scales with the power of the size of the problem, which here is n, right? N by n matrices. So matrix multiplication is easy. Unfortunately, most problems can't be solved in polynomial time. More typical is exponential time, where the running time grows exponentially in the problem size. So, and that's pretty bad, right? So for example, like say matrix multiplication required exponential time, then already for 100 by 100 matrices, we'd be talking about e to the 100 operations, and so we wouldn't be able to do it in the, within the lifetime of the universe so far. Okay. So exponential problems are really hard. Just for fun, I'll mention that there are even uncomputable problems, which can't be solved in any finite amount of time. Somehow we run into those less than we run into the exponential ones. Now, somewhat confusingly, and I just mentioned this for fun, so not central to the talk, but just for fun, although we know that most problems require at least exponential time, it's really hard to show that for any particular problem because, well, maybe someone else could just come up with a polynomial algorithm and they're smarter than you. Right? It's very hard to prove that no algorithm exists that solves the problem with polynomial time. And so that's this famous p not equals to np problem. In fact, if you can prove that for a wide list, any one of a wide list of known algorithms, then you can get $1 million. So go get them. All right, so that's classical computing. Good. Now we finished computer science. On to quantum computing. So a quantum computer is a new kind of computer, at least hopefully, that we might have soon, which is based on what are called qubits instead of bits. And the nice thing about a quantum computer is that some of the problems that were hard, exponential time, on a classical computer can be polynomial time on a quantum computer, which means we go from unsolvable to solvable. The classic example of that is factoring. So if I give you some big number and I want to know its prime factors, there's a polynomial time algorithm for doing that on a quantum computer. But on a classical computer, the best algorithm that we know is e to the n to the 1/3, where n is the number of digits of the number. So it's exponentially hard. And so if you could do that, right, you could defeat all of online, security and crash the world economy. To me, that's not the most interesting application. And that's the one we usually talk about. Who cares about the world economy? The president is destroying it anyway. So, okay, now what's a qubit? Well, for a classical bit, the state of the classical bit is either 0 or 1. Okay, that's what we were discussing before. For a quantum bit, so here's this funny notation. The idea is that the state of the quantum bit can be a sum of the 0 state and the 1 state with complex coefficients a and b, which are required to obey a squared plus b squared equals 1. Okay. And in fact, in the notation we used before, this a and b are the thing I called the wave function. Remember, in the distant past, we had psi of x that told us the wave function for where our particle was. So this is the bit version of that. A and b are the wave function. And so that's for 1 qubit. For 2 qubits, now you have the 2 classical bits. You have 0, 0, 0, 1, 1, 0, and 1, 1. But for 2 qubits, now instead you can have an arbitrary linear combination of these with these complex coefficients, but again obeying this rule that the sum of their squares is 1. And so again, this is like the wave function. A through d are the wave function for 2 qubits. And so in essence, the reason why a quantum computer is powerful is because, if you think about it, there's a lot more information in these complex coefficients, a through d, than there is just in 0, 0, 0, 1, 1, 0, or 1, 1. Right? The classical thing, there's just 4 options for what the state could be. But here there's a continuous infinity for what the state could be. So there's a lot more information in this state. Now, just so my friend Scott Aronson doesn't get mad at me, I have to say that actually, that makes it sound too powerful. That makes it sound like it can do almost anything. Most of the time, it's hard to access that continuous infinity. You need to have situations where you have a very clever algorithm in order to be able to actually benefit from this. But when you do, this is what you're benefiting. Okay, now here's the slide about the weirdness of quantum mechanics. So, the mathematics look simple, but you might be thinking, okay, Daniel, come on, what does it mean to say that the bit is in the state 0 plus 1? What can that possibly mean? That's a good question. Good question. So certainly, each of us, right, we know, whether we're in North America or Asia or somewhere else, and at least I've never found myself in a situation where I'm in more than one of them at the same time. I suppose in principle you could find yourself in a situation where you don't know which one you're in. But, and in fact, that's a slightly better analogy. Right? Like a better analogy would be a situation where you know you're in one or the other, but you don't know which. But actually, that's not a perfect analogy either, because that doesn't distinguish between 0 plus 1 and 0 minus 1, whereas quantum mechanics does. So somehow, ultimately, we just have to accept that the fundamental ingredients of the universe work in this funny way where there's difference between 0 plus 1 and 0 minus 1. And that's just always going to seem strange to us because this distinction is always washed out in our daily experience, as I'm about to explain in a minute, by something called decoherence. So, if we were, little atoms, then maybe this would look more intuitive, but since we're not, it doesn't. And in fact, when I talked yesterday, I had quite a bit of that. Okay, now, you may ask, okay, so I mentioned several times that we don't actually have quantum computers yet, so why not? It's actually for the same reason that we don't find quantum mechanics intuitive, as I just said, right? It's because it's hard in practice to preserve the distinction between 0 plus 1 and 0 minus 1. So in any complicated system, this information is lost almost immediately by decoherence. So let me try to say why. So classically, if you're trying to protect information against noise, say you're trying to communicate with the Voyager satellite, out past Pluto, it has a very small radar dish. You just send the classical message once, who knows whether it'll get received. Even if it gets received, maybe the bit will get flipped by accident. So what you do is you send the bit 100 times, right? You send 100 zeros or 100 ones. And then when Voyager listens, it listens to, it gets, maybe half of those or something, or 3/4 of them. And then it just does majority vote and guesses which one I actually tried to send. And it's pretty unlikely that the error is going to flip more than half of them. And if it is likely, then you just send even more so that it is. So that's called the classical repetition code. And that's how you protect classical bits against noise. So unfortunately, with quantum bits, that doesn't work, right? So we could try to do the same thing. We could try to, instead of sending A0 plus B1, we send A times a whole bunch of zeros, plus B times a whole bunch of ones. Okay. But the problem is that say an error comes in on any one of the qubits, which flips 1 to minus 1, by flipping B, sorry, flips B to minus B. Well, I only need to hit any one of the qubits with that error, and that flips this sign here. Okay? And so this quantum repetition code is bad because it doesn't protect against an error that flips the sign from 0 plus 1 to 0 minus 1. And that's essentially the phenomenon of decoherence. You just have to, tap any one of them, and you lose the phase coherence of this position. So that's why we don't like quantum computers. Very hard. So here's a sort of fanciful illustration that I'll use again in a minute. So we can illustrate it like this. I got a bunch of qubits, and gremlins are coming, and they're going to mess up a few of the qubits. Not too many, but some of them. And I want to store the information in some way that is independent of what these sort of localized gremlins can do. So in fact, there is a way of doing this, which is called quantum error correction. So we can't use repetition, as we just discussed, but there's still a way of using redundancy, where we encode a logical qubit into a larger number of physical qubits. And here's a simple model. Actually, the simplest model, you use a qubit instead of a qubit, so it's a 3-state qubit at 0, 1, and 2. So this is a simple example of a quantum error correcting code. And you can actually show, although of course I won't show you now, that this protects against an arbitrary error on any one of the qubits, either a bit or a sign flip. And so this is an example of how to protect quantum information from localized gremlins. Now to actually implement this, you need the probability that a gremlin disrupts any particular qubit to be down to about 1 in 10,000. And right now we're at about 1 in 1,000. We're getting there. Getting there. Hopefully in 10 years. All right, back to quantum gravity. We're almost done. What we realized in 2014 was that this problem we had before in holography, which I'll remind you, was how was the central degrees of freedom behaving as they were independent of all the boundary degrees of freedom, is really a problem in quantum error correction. And here's how it works. There are the gremlins, they live out of the boundary. And say this gremlin is going to disrupt these 2 qubits here, that's all they can be. And so if there's something in the gravity theory that's over near the boundary, then they can mess it up, and they're happy. See the smiley there? The CGI budget was very high. On the other hand, this person who's in the middle, they can't be messed up, even by a rather big gremlin, so the gremlin is kind of happy. So somehow they're protected from the error. And so information near the boundary is easily corrupted, but information in the center is not, and it's protected by a quantum error correcting code. So for example, this 3-2 trick code I mentioned, we can view it as a simple model of quantum gravity. The logical qubit lives in the center, and it's encoded into the physical qubits at the boundary. In fact, we were also able to show that standard limits on how good quantum error correcting codes can be match up precisely in the gravity theory to the formation of black holes. So in other words, space-time emerges from the redundancy of quantum error correction. And when this breaks down, a black hole is the result. Okay. Second to last slide here. So what does this tell us about the black hole interior? Right? That was the problem we started with. Too many degrees of freedom in the black hole interior. Now, recall that the basic problem we have is that the black hole entropy formula doesn't allow for enough degrees of freedom to give a nice local description of the interior. That was the problem we had, was the entropy goes like the area of the volume. So encoding language, what's happening is we're trying to encode more degrees of freedom, the effective, the local degrees of freedom in the interior, into fewer, which is the opposite of redundancy. Right? What we saw with codes is to have a good code, you want to go from fewer to more. You want to send the message 100 times. Right? But here somehow you want to have a big message and send it through a small channel. And then you can worry that the emergence is somehow being messed up with the interior, and that's kind of the essence of Hawking's problem, the black hole information problem. So how can this be acceptable? And so what we've realized in the last few years, so this is say 2022 or so, with collaborators of course, is that we developed a theory where a code which is not redundant is still actually able to preserve information, provided we only ask about information that's not exponentially complicated. So here we get back to the complexity theory, right? There are simple things and complicated things. Complicated things are exponential. And the idea is that that interior looks like it's local as long as you only ask about simple things. But if you ask about complicated things, then there's a massive breakdown. And we were able to work out the mathematics of that. And we further show that this kind of code can reproduce many features of quantum black holes. Okay, so obviously there's a lot more I could say about all this, but I want to close with some crazy thought, although it seems a bit less crazy instead. So perhaps someday in the not too distant future, in our everyday lives, we'll have quantum devices in our pockets, here's one, that work because they're simulating quantum gravity to avoid decoherence. So that would be an engineering application of quantum gravity. I felt that this science is done by people, so here's something.
There's plenty of time for people to, if you want to select three hands yourself.
Sure, okay. That's right. Don't be shy. Yeah.
Yeah, so essentially I want to ask about the ADS slide,
Yeah.
where we took assumptions, right? And we had an assumption where what happens in the middle has to be approximated to what happens in the boundary. So, but in your yeah, so in the next slide, second point of the next slide, you mentioned that what happens in the boundary, what happens in the middle has to be approximated to what happens in the boundary. But in your approximation to QEC being quantum error correction being a model for these approximations, we when you showed that the information at the middle of the model is being is not being disrupted, rather it's retaining its information, then that means it's effectively not an approximation of the boundary, right? So
well, that's the puzzle, right? So it's not that it's an approximation of the boundary. So the boundary is all there is. Okay? So there must be some big complicated observable in the boundary that tells you what's going on in the set. If that wasn't true, the theories wouldn't be useful. Right? The challenge is, how can that big complicated observable, which is just made out of those local boundary degrees of freedom, behave like it's not made out of it? Behave like it's independent function. Really it isn't. Yeah, and that's the problem that the code solves, because like in this Q-trip model, for example, there's three states of what was going on in the bulk. They were just states of the three boundary Q-tips.
Yeah, can you hear me?
Yeah.
Well, first off, I wanted to thank you for your talk. It was very approachable and very understandable. So, I wanted to ask you about when you mentioned black hole temperature, the Hawking radiation.
Yeah.
What I understood was that this was caused by vacuum fluctuations at the boundary.
At the edge of the black hole, yes.
Right. So then, my question is, wouldn't we be measuring the temperature of the fluctuations of the vacuum and not necessarily the black hole?
Yeah, but if you just sit far away from the black hole, and you say, I don't care what's going on right near the black hole, I just want to know what I feel out here, you'll see that there's this flux of radiation that's coming out.
Caused by the black hole.
Yeah, caused by the black hole. And now we can debate a bit about did it come from the black hole? Did it come from the space right around the black hole? It's a little bit hard to pin down, but it's clear that if you stand far away, that flux is coming out, and so the mass must be going down.
Okay. Thank you.
So you started off and you argued everything had to be local, and you invoked special relativity for that.
Yeah,
And yet in the end, you came up with this idea that everything is driven by the surface.
yeah.
And so how is that consistent with your earlier argument about special relativity?
Yeah, well, that's exactly the question, right? So I argued that special relativity tells me that things need to obey locality and be independent, but then I argued that they can't be. And so, that was what I tried to say, Ken, is that if the code is sophisticated enough, then it can fake that it obeys locality, and then it will look relativistic to a very good approximation. And then, that's really all we should have asked for. Because we never know anything to perfect accuracy. We just need it to be good enough that we wouldn't have already seen violation. Yeah, Ted?
Can I ask you a question? So, it's a profound proposal that the space and time in the bulk are emergent and locality is emergent.
Yeah.
But the example you showed us that implements that is based on a local field theory on the boundary that has not emergent space and time, but pre-existing rigid space and time.
Yeah.
So that bothers some of us, I think, and I'm wondering if it bothers you and what you think about it.
Well, so that time is boundary time, right? But there's also the time in the bulk, which is generated by the Hamiltonian constraint, and that's emergent.
Absolutely, I'm not contradicting that emerges, I'm just saying, if you're telling us that, the future holds in store for us a formulation of fundamental physics, in which all space and time is emergent,
Yeah.
then I shouldn't be basing the theory on a rigid space and time at the boundary.
Right, that's right. So in ADS-CFT, that's why we figured out ADS-CFT first, is because it's a bit less emergent. That asymptotic boundary is solid.
Yes, so what I'm asking
And then
is,
it's
what
only
would
the
be
inner
more
part.
emergent? Where should we look to find the more emergent version?
Well, you could go to my talk from yesterday and think about a universe with no asymptotic boundary.
Well, yeah, I wanted you to say something about that.
Yeah. Did I do that?
No, I
just did. I see. Okay. Yeah. So indeed, right. I mean, so let me phrase Ted's question in a more insulting manner.
Who are you insulting?
So, I gave all this talk about the negatively curved ADS space. Okay. Does anyone know whether our space-time is negatively curved or positively curved? Positive, as far as we can tell. It has de Sitter, as far as we can tell. So, so why did I spend the whole talk talking about this thing, the space-time that we don't live in? Well, that's the spherical cow thing in physics, right? So I talk about the thing that I understand, and then you try to build from that towards things that are more realistic. On the other hand, this business of having this very rigid boundary at infinity doesn't seem so realistic, and that was really crucial to this proposal. So we would like to try to generalize it to more realistic space-times, and we're trying, but I would say we're still confused. We don't understand it at the level that we understand it. So hopefully we will understand it better in the future. Maybe here and then.
Thanks for a really nice talk. Could you comment on these ideas that as black holes evaporate, they leak information about the things that have fallen in, but in a way that's very hard to decode?
Yeah, so that's part of the story. So that's the more sort of conventional phrasing of the information problem, is you say that when the radiation comes out, it looks like it doesn't have any information about what came in. But this code I talked about at the end for the interior that goes from more to fewer has the property that what you fed into the black hole does eventually come out in the Hawking radiation in the scrambled form. Yeah, so if I had another half hour, I would develop that more. But yeah, that's part of the story. So that's something called unitarity or information conservation, of which I am a person. And maybe here and then wrong. Sorry. Okay, go ahead.
In the analogy to quantum error correction, I guess the idea is you've got your real or physical qubits on the edge, and then the interior is your logical qubits. But why are you having more logical qubits than physical qubits?
Good, so in that example I didn't, right? And so that's why that example, this example, right, is going from fewer to more, that's more conventional, and that's why we understood this example in 2014. The black hole interior, to go from more to fewer, you have to ask about the interior of the black hole. Because in this story, right, I said the black hole comes from a sort of failure of the code, right? That was the 2014 understanding. And that's correct if you want the code to go from fewer to more. But actually, we think that at least sometimes that black hole does have some space-time inside of it that we should be able to understand. And then I understand that I need to do this more to fewer. But it's only for the interior of the black hole. Yeah, okay, maybe you know. Okay.
Well, so that famous space, the negatively curved space, has this funny geometric feature that instead of area growing much more slowly than volume, our space, it actually grows at the same rate.
Yeah, that's a bit
So
of
the
a
level of power knocks is far less.
Well, no, but you have to look at the power of that zone, right?
Which was that?
G unit.
Okay.
Yeah, so the area and the volume, area in Planck units and volume in Planck units have different powers of G. So in the CFT, that's different powers of N. Sorry, this is an answer for Ron.
So you, I was
so
actually
the-
thinking if it was
So the power of N is different, even though the scaling is area versus volume.
do you feel that we have got, this is a toy model of this remarkable thing that hopefully everybody in the audience gets, which is that as you make a sphere bigger, the volume grows much more rapidly than area in 3 dimensions, and it's purely a geometric statement about H theory and whereas that aspect is just not true in one example.
Yeah, so when you make this model more carefully, you have to say that there's a lot of degrees of freedom flowing on these links and then n gets involved. You really have to see it in this model. I agree, that's an annoyance of big test. Here, and then
I just wanted to follow up on Ted's question. So given that this work was done with respect to entities that are space,
we're getting close to the truth. Well, we can carry on. I'm okay. Go ahead.
yeah, so this was done in entities of space, and bigger than the center. So what, if anything, can this tell us about what these results might say for our universe and how entity related?
Yeah, we're working on it. Yeah, I can't say anything with great confidence now, but we're working hard on it.
So this is probably a very naive question, but it's light travels like you can curve light around like a massive body, and when space time is like a positive curve, then a negative curvature would light curve away, or like what would happen? I don't
No,
even
it's
know.
kind of the other way. So negative curvature is more, well, let me think how to say it. Yeah, it's a bit subtle. So the way negative curvature works is actually if you shoot a light further away from you, it actually springs around and comes back in finite time. Whereas positive curvature means the universe is extending exponentially, and then the light gets carried away from you and you never see it again. So maybe we should do one more and then
Yeah, so if you believe that time is emergent, then you have to believe that you cannot say which event happened first and which happened second. And that's really important because it tells you how to apply the physical laws, right? So causality is a property of space-time. If you say time is emergent, then causality is emergent, and you lose this partial ordering.
yeah, that's right. That's right. And then I have to hope that the effect is small enough in daily life that it doesn't ruin a sensible experience.
Well, you say that you believe that the whole universe is
Well, so the thing that has to
structure,
be
so it's
the
not
thing
a
that
small-
has to be exactly true is boundary causality, because we have this rigid structure at the boundary. And so to the extent that there are causality violations, they usually involve things that are behind horizons, in the interior of the black hole, and then it kind of keeps the problem.
But isn't the ordering of events what we call time? How is that emergent?
Well, if time is emergent, that has to be also, right? I agree it's concerning to say that space and time are emergent, but we seem to be being forced into this.
Well, anyway, yeah, it is, it is a duality. It doesn't say it's an equivalent description. It doesn't say one is deeper than the other.
Well, it's, right, but in some, no, but when you say something is emergent, you are saying
You
one is
said that.
deeper. Yeah, I did, no, but I think the classical picture of space-time there is emergent. It's not like it's equal to the boundary. It emerges from the boundary in some approximation in certain situations. The thing that's exactly dual is the non-perturbative quantum gravity in the bulk, which I don't know what that is. Maybe it's some form of string theory that we don't currently understand. But it's not just, matter fields and metric talking to each other in a third relation. And that's the description I'm trying to understand here, is the description that we see around us.
All right, probably there are more questions, but I think we should stop and thank Daniel.